Hi everybody, and welcome to the CSMR Soft Matter Seminar Series run out of New York University. I see we have people here from all over, which is just phenomenal. I welcome everybody, and it's really, really good to see you. So I'm very happy today to introduce our speaker, Wilson Poon. So Wilson is a professor of physics at the University of Edinburgh, but he's not just a professor of physics. He holds the chair of natural philosophy, which for physicists is really going back to our roots. And this is a particularly noteworthy honor because at the University of Edinburgh, the chair of natural philosophy was established in 1708. So that's right back at the dawn of our field, and is bestowed by election. So the university really has singled Wilson out, and deservedly so. So he got his undergraduate degree with first-class honors and doctoral degrees, both in physics or various aspects of physics at Cambridge University from various colleges at Cambridge University. And he also did some of his postdoctoral work there before he took his first faculty appointment at the University of Edinburgh. So he's been elected a Fellow of the Royal Society of Edinburgh in 2004 and was elected to the chair of natural philosophy in 2016. So as you probably all know, I mean, Wilson's research program has focused on the phase behavior and rheological properties of complex fluids, most notably colloidal dispersions and colloids in combination with other types of soft materials like polymers, liquid crystals, and surfactants. And his studies have produced beautiful and really carefully crafted phase diagrams for these complex systems in equilibrium, and also comprehensive surveys of their non-equilibrium behavior, most notably like the kinetics of phase separation and the emergence of glassy states. And most recently, he's broadened his scope still further to encompass collective behavior in active soft matter systems. And all of this work has been really important for building our field's understanding of the mechanisms of cooperative behavior and self-organization in many body systems. And it's fundamental work that's been recognized with a Wolfson Research Merit Award from the Royal Society, and of course the Sam Edwards Medal from the Institute of Physics, among many other honors. And so Wilson's work, has had a huge influence on our field. And it's also been really useful for guiding industrial applications of complex fluids. And so Wilson's been exceptionally active in transferring knowledge and technology from academia into industry, including founding the Edinburgh Complex Fluids Partnership, specifically for this kind of activity, and also his group's participation in the International Fine Particle Research Society. So the COVID-19 catastrophe has affected all of us, has affected all of our research programs, and it also has turned Wilson's attention to a new class of problems, specifically the hows and whys of infectious disease transmission in the pandemic, and more specifically, why and how soft matter processes are to blame for the catastrophe, and how soft matter science can help. So rather than try to second guess his game plan, I'll turn the microphone over to Wilson.
Right. Thank you very much, David, for the welcome. I both like and dislike giving these virtual seminars. I mean, I far prefer to be in New York. I have very fond memories last time I visited for a month. But on the other hand, it's absolutely wonderful to see faces that I don't associate with New York. I have Canadian friends there. I have people from Texas that I know. So yes, it's absolutely wonderful that these virtual seminars are reaching a very large geographic audience. So let me attempt to do the technology and share my screen. Let me just see what happens. Now, can you see my slide?
So we see your slide. That's perfect.
No, but the wrong slide. Oh, let me.
No, we may be seeing the wrong slide, but we're seeing it correctly.
It's the wrong talk even.
And the wrong trousers.
In some versions of this talk, I include references to the American election, but I figured that you probably don't need to hear about it, so I took those slides out.
Thank you.
Anyway, so I'm going to talk to you about soft matter physics and the COVID pandemic. And here is the word ignorance here, because I'm basically telling you what I don't know, and in fact, what I suspect no one knows. So let's just remind ourselves what soft metaphysics is. The vast majority of you don't need reminding. So soft metaphysics studies complex fluids. These are liquids with bits in it. So these are the bits. And of course, the bits undergo Brownian motion. And so you know all of this. Why am I reminding you of this? Well, I'm reminding you of this because it is important to realize at the outset that viruses are in fact quintessentially soft matter objects. So here's a bacteriophage. It's a typical bacteriophage, and their sizes are in the colloidal scale. So bacteriophage is nanoparticle. I mean, I'm showing you that one simply because I like it, because it looks so much like a lunar landing module. But this is the coronavirus. Coronavirus is an envelope virus. So the size again is in the colloidal domain, a little bit bigger than a bacteriophage, but still a nanoparticle. The size is in the colloidal domain. And each of these viruses is surrounded by a lipid bilayer. So these are these kind of objects. And of course, lipid bilayers, it's all kinds of proteins embedded in them, and there is some suggestion that they are locally ordered on a lipid bilayer. And of course, the coronavirus is not the only. That is an envelope virus. The flu virus, which is usually the virus that we're concerned with this time of the year in the northern hemisphere. The flu virus is also an envelope virus, as is the herpes simplex virus, which is the thing that gives you cold sores at the corner of your mouth. So envelope viruses, especially because of these lipid envelope on the outside, are quintessentially soft matter objects. All the things that soft metaphysicists are interested in are present. They are lipid bilayers, they are polymers in the form of the genome, and of course, the entire object is on the colloidal scale. So here's a picture of what happens. The virus, of course, starts inside the body of an infected individual. And so here's a schematic of that virus. So this virus starts off in the lungs of an infected individual. Of course, what happens to the virus inside the body is the concern of hospital medicine. This is what doctors have to deal with. Patients present themselves with the viruses, having done things in their bodies. And there are plenty of soft metaphysics about the cellular interaction of these viruses. I won't touch on that in this talk because it will make it too large. What I'm largely concerned with is the rest of it. So, when an infected individual talks or breathes or sneezes or coughs, and the virus gets out, and everything that comes out up to the point when it enters another body is, of course, not so much the purview of hospital medicine, but it becomes the domain of public health. And here we're dealing with issues of transmission, how it gets through the air directly to another body or through surfaces to another body, all with matters of disinfection and protection. Once the surfaces are contaminated or our hands are contaminated, how do we disinfect, or how do we protect individuals from it? Various kinds of personal protective equipment, masks, gowns, etc. Okay, so I will be largely talking about the soft metaphysics of this bit. Okay, so I'll be dealing with this lot rather than this lot. Doesn't mean that this is unimportant. It just means that I don't have time to deal with it. Okay, so we got to that stage at the beginning of the pandemic last March when the lockdown happened. A whole bunch of colleagues and myself in Edinburgh sat down and decided we want to do a survey initially for our own purposes of what is known about the soft metaphysics of the COVID pandemic in particular, but also of respiratory pandemics in general. And very rapidly, it turned from exercise to finding out what is known to discovering what is not known. So I would like to think of the paper that you eventually wrote, and is now on, you can get it online at Soft Matter. The paper that we eventually wrote turned into what I call Encyclopedia of Ignorance. By the way, those of you who are about the same age as me, I remember in the late 70s, someone actually did publish 2 volumes with that title, called the Encyclopedia of Ignorance. In fact, looking at these 2 volumes were quite important in getting me into science, because I quite like the fact that there were things that were not known. So it turned into an exercise for ourselves of, to quote Donald Rumsfeld, turning unknown unknowns into known unknowns. So what we managed to do when we wrote this article was to write down, or if you like, to crystallize a few questions that soft matter physics need to find answers to if there's going to be a complete picture of knowledge of how these pandemics spread. So we hope to turn a lot of unknown unknowns into known unknowns. In the process, we also sifted out a few things in the literature that must be wrong. So just because it is slightly amusing, I will give you one example of this, and I'm going to get on with the rest of it. So the example that we found it must be wrong is, one of the most basic things we want to ask ourselves at the beginning of our exercise was, how many viruses are in an average respiratory aerosol droplet? So, we cough, we speak, we breathe. There are these droplets that come out of our respiratory systems. So how many viruses are there per droplet? So very soon, we trace a number of, so there's a number quoted on the internet, and eventually we found a reference to it in a textbook, in a widely used textbook. This is a modern textbook, this is not medieval. It's the third edition, they had plenty of time to get it right. So we found this textbook, which is widely used in certainly in American campuses. So here on page 396, we find these words. So these words refer to the influenza virus. It tells us that there are between 100,000 to 1 million viral particles in each droplet. And this estimate is in fact widely reproduced in lecture notes, in lecture notes that I say even belong to Ivy League universities in the States. So this is a widely quoted number. In fact, a lot of people quote the million figure, that there are 1 million flu viruses per droplet. So we were very curious about this number because it sounded quite high to us. And in fact, the book itself tells you it must be wrong, because it tells you the infectious dose of influenza A is between 1,000 to 200 infectious virions. So in fact, it takes only apparently about 1,000 viruses of the 1,000 particles of the flu virus to infect you with the disease. And this one I checked. This one is widely reproduced in experiments. So if it only takes 1,000 viruses to infect me, and every time someone with flu coughs, it generates droplets with 1 million viruses in it, all of us should be having flu all the time, which is self-evidently not true. So this is amusing because I think this is a piece of a biologist talking to a physicist gone wrong. Because you can imagine a biologist coming to a physicist and ask, how many flu viruses can there be in a droplet? And some physicist estimated the random closed packing limit for flu viruses in a 10 micron drop. If you go and work out how many 100 nanometer spheres you can fit in a 10 micron drop, amusingly, you get 1 million. So I suspect this was an upper bound given by a physicist to a biologist of random closed packing in a droplet, and it get reproduced as fact in a biology textbook. So we thought that was mildly amusing, except for the fact that the number is widely reproduced. So in our exercise, in writing that paper, we found a few things in the literature that must be wrong, but mostly we found a dangerous ignorance. And ignorance reproduces assumptions, and assumptions often becomes fact when they become quoted. And let me show you a few of those. So let's talk about transmission. Let's talk about what happens in the very first step. So, it's very easy to draw this picture. An infected individual has viruses all the way along his or her respiratory tract, and they breathe, they speak, they cough, they sneeze, and then there's all these aerosol droplets that come out of the respiratory system. So the question is, what are these? I want you to just pause there at that point. I want you to pause. Just very briefly think about what is your mental picture of what these droplets are. What do you think these droplets are? So I want to pause there because because of Sherlock Holmes. So many of you may know the Adventure of Silver Blaze, because in it, Sherlock Holmes had this famous conversation with Gregory, the Scotland Yard detective. Gregory, is there any other points to which you wish to draw my attention? Holmes, to the curious incident of the dog in the nighttime. Gregory, the dog did nothing in the nighttime. Holmes, that was the curious incident. In other words, the curious thing for Sherlock Holmes was that the dog didn't bark. The detective didn't think that was strange, but Sherlock Holmes thought it was very strange. This curious incident of the dog that didn't bark at night time. Now, I want you to think about what's in those droplets because of this. In the entire discussion previously of flu pandemics, now the coronavirus pandemic, it is assumed that viruses can survive in these droplets for finite time. They need finite time to go to another person directly or indirectly. It is always the silent assumption is that that is obvious, that viruses should be able to survive in these droplets for finite time. But I think actually that is the curious incident. Why is that curious? Well, this plot could have been done by James Clerk Maxwell, our local hero in Edinburgh, born and bred. This is the evaporation time of water droplets of various diameters in an atmosphere of different relative humidity. It's a classical calculation that was first done by James Clerk Maxwell, amazingly, in his article for the Encyclopedia Britannica on diffusion. But anyway, that's by the by, at 20 degrees C. So you can see that these droplets evaporate to nothing. They completely evaporate in significantly less than a second. Now, what happens to desiccated viruses? Well, here's a paper in PNAS about 10 years ago on the fate of desiccated bacteriophages. So here are the results. Here's a bacteriophage. I can't remember which, but you can read the paper and find out which one this was. Here's a bacteriophage, a virus that infects bacteria. So if you do the topography, if you scan a line across here and see how high this virus is above the surface, you find that they are sort of 42 nanometers high, and that is indeed the size of the viral capsid. But when they desiccate these bacteriophages, they just deposit them on glass and either dry them in air or vacuum dry them. And you measure the topography, what you find is that there are two families, either this high or this high, and simultaneously they also see the genome of the virus spat out. So their interpretation is that these heights are due to viruses that have collapsed a little bit, collapsed by about, 25%. And then that collapse is due to the fact that they have spat out their genome. But there are other virus particles, such as these, seen here, where they not only spat out their genomes, but actually they're completely collapsed. So in fact, this 5 nanometers is roughly the thickness of 2 capsids. So viruses do not survive desiccation. At least their genome gets spat out, possibly they entirely collapse. Now, these are for bacteriophages, but people know that envelope viruses are generically softer. So mechanically, viruses like the flu virus or the coronavirus are, how do I put it? They should be more susceptible to this kind of collapse on desiccation than bacteriophages. So I go back to my Sherlock Holmes question. These droplets, they contain viruses, they leave the body. These droplets, if they're water drops, they evaporate in less than a second. The viruses should be completely desiccated. What's going on? Why do they survive at all? Why is it possible for airborne infections to be airborne to be infectious? So of course the answer is that these are not virus in water droplets. So you remember I asked you what is your mental picture of these droplets. I wonder how many of you have viruses sitting in droplets of water in mind. So the red is water, the black are the viruses. So it's very easy to picture these droplets as just viruses in water. I mean, soft matter physicists like studying the evaporation of droplets, like that evaporation of colloidal drops. Many in the audience have worked on it, so have I. So it's very easy to map our thinking to what we know. In other words, this is the famous coffee coffee stain experiment. These drops fall on the table, leave a coffee stain, they leave a coffee ring, that kind of thing. But these droplets are not like that. But we're not the only people who think of these droplets as being like that. So in other words, it's very easy to think of these droplets as just viruses in water, and then they rapidly evaporate according to Maxwell's theories, and then all you're left are the viruses. Let me show you that this is exactly what's in mind of the people at NIOSH. What does it stand for? I can't remember, but it's one of your agencies. It's the one that is in charge of drawing up the procedures for testing N95 masks. So this is a direct quotation from the procedures from the NIOSH website for how one should test these N95 filters. Respirator filters will be challenged by a sodium chloride aerosol at 25 degrees, a relative humidity of 20 plus minus 10%. So what does it mean by challenged by a sodium chloride aerosol? What they mean is this. What they mean is you aerosolize, nebulize a salt solution. I think it's 0.15 molar to be close to physiological, I think, but never mind, you basically have a salt solution that you aerosolize. These drops, again, Maxwell and a little bit of Kelvin, sorted out of physics, they evaporate very quickly to leave just salt nuclei. And the distribution of these nuclei is specified that it has to be about like this. So this is a paper that I found that has done some experimental testing of these N95 mask filter materials. And the sodium chloride distribution has to be something like this. There's further specification further down this document that says what the median should be and what the standard deviation should be. Now, the reason why they wanted the distribution to be like this and why they specify N95 as the standard must be that this peak is slightly smaller than the virus diameter. The virus diameter is about 100 nanometers. So the picture that these people have in mind is this. You have droplets. The virus clearly is modeled by the salt. And in the end, when the water is all evaporated, all you're left with the viruses. And the viruses are clearly what infect us. And so the filter had better be able to filter out the viruses. That's the picture that the entire literature, and I mean the entire literature, barring a handful of papers, is that infection is due to people sneezing out viral droplets in water. The water evaporates, I'm left with viruses, and the viruses on their own, as bare viruses, infect us. But these are not like that. These droplets are not like that. These droplets come from our lungs. Our lungs are covered by a layer of mucus. Mucus is a big component of mucus is mucin. Mucin is a glycoprotein, which means it is a protein backbone with sugar chains coming off it. So this is a glycoprotein, highly charged with a lot of, for example, COO minus groups and phosphate groups, etc. And the molecular weight of these can be frightening. I mean, the molecular weight of these things can be up to a few 100 million. Of course, there's also a lot of DNA. The DNA come from the epithelial cells having died, and so their nuclei shed the DNA, and the DNA get mixed into this mucus. There are also lipids, again, from the membranes of the dead cells. Of course, there is salt. Undoubtedly, there is salt, but not just sodium chloride, various salts. And of course, they bear viruses. But it's very, very much more. These droplets are very, very much more than water and virus. So these are, if you like, biopolymers, salt, lipid, virus droplets, minimally. And the frightening thing that we discovered was that there's almost no literature on composite droplets like this. Okay, so I'll say it again, there's almost no literature. In fact, I found precisely one paper. I will show you this paper later because I'll refer to some of his results and show you why this is important. But there's almost no research on droplets, either the real thing or in the sort of way that we usually operate as soft metaphysicists, model droplets that have these kinds of components, high molecular weight polymers, surfactant, and salts. So, I mean, most of what I have to say from now on is to try to convince you that the compositional complexity of these respiratory injector has important consequences. Almost none of it is my own work. but I'll show you a little bit of what we've done at the end. So let's think about just how these droplets are formed in the first place. So this is work from Bariba's lab in I can't remember where she is, but anyway. So this is a high speed photography of someone sneezing. This is a side view. This is a top view. The scale bar here, let's just see how big it is. That's 1 centimeter. This scale bar is 1 centimeter. So what I want you to notice is there are these long threads. So I'll take it away and you can see it. Now I haven't created it here. There's a long continuous thread that is about 8 centimeters long. And basically that's a single molecule. It's a single molecule of mucin. And such threading is very, very characteristic of high molecular weight polymers. So the moment you take a high-speed photograph of this, you can instantly tell that these long, thin threads that can survive hundreds of milliseconds tells you that there must be very, very high molecular weight polymers present, and that their presence is important. Okay. So how important they are, you can tell from this wonderful paper from Gareth McKinley's lab. And you can hear his talk if you go onto that website from the Journal of Non-Newtonian Fluid Mechanics. And the results is published in this PRL quite a few years ago. But they were paid by a paint company to think about the spray drying of paint that has a lot of polymer in it. Okay, so this does not only have particles, the pigments, but also a lot of polymers in it to modify the rheological properties. So they were actually thinking about the fragmentation of viscoelastic liquids. They weren't thinking about COVID crisis at all. But what they discover is summarized in this plot. What they discover is this. So this is the size distribution. The x-axis is droplet size normalized by the average droplet size. So this is the probability distribution on a log scale. Droplet size distribution of various kinds of model paints. So these are basically the polymer component of paint. In other words, it has high molecular weight polyethylene oxide at 2 different molecular weights and 2 different concentrations. Now the dotted line, the red dotted line, is a log normal distribution. And that's what you will find in aerosol textbooks. Okay, aerosol textbooks will tell you that aerosols are distributed log normally. What you find instead is this. So when Gareth's group did droplet size distribution with a Newtonian liquid, the black is what they get. Okay, the black is from spraying out a Newtonian liquid. And that fits a gamma distribution, a single component, single parameter gamma distribution. Gamma distribution using 2 numbers, alpha and beta, but here alpha equal to beta. So it's a single parameter gamma distribution. It fits a gamma distribution of n equal to 4. But the amazing thing is, it doesn't matter which of these 2 molecular weights, 300K or 1000K, a million molecular weight, whether it's 0.1% or 0.01%, various concentrations, various molecular weights, all lie on the same curve, which is this same gamma distribution, but now with gamma with n equal to 4. Okay, so what they find is that provided the viscoelastic solution, provided the polymer satisfies certain very minimum characteristics, then independent of molecular weight and concentration, the droplets that come out of spraying the solution fits a universal gamma distribution, provided you normalize the diameter, with n equal to 4. Now, I think that is a very significant finding because Gareth, if you go and listen to his talk in the website on the Journal of Non-Newtonian Fluid Mechanics, he shows you that he used some data from Bariba's lab to show that distribution also fits the droplet data from someone sneezing. And that's not surprising because the PEO here is the place of the PEO is taken by the mucin and possibly the DNA, but almost certainly the mucin, a very high molecular weight in the droplets, leads to them fragmenting or the ejector sheet fragmenting into droplets that fits onto this gamma distribution. Now that is important because you can look at the literature and there are as many distributions in the literature as there are papers. So here's a random paper that I found from Journal Royal Society Interface where they got someone cough into a box and they count the droplets. So this is all the droplets that they count from getting people count slowly in English from 1 to 100. So what that's about a minute of speaking. The numbers 1 to 100. Okay, so this is me replotting the data in probability distribution, normalized by some average diameter. The dots are the data points, and here is the gamma distribution. I didn't fit it very precisely. I did it by eye, but here's the best gamma distribution I can put in by eye. And the value of this is that if Gareth is right, if the droplets produced by sneezing and coughing really should fit a gamma distribution, then you can tell that these measurements must be defective. These measurements must be wrong. In fact, there are some data points down here. You can see it hiding there. There are actually data points that are measured at close to 0, and they're far too low. So these data points, these ones, should be quite a bit further up. I mean, but the point is, all of the disagreements happens down here, and that's what you expect, because the small droplets are harder to capture and harder to measure. If they're going to make mistakes, you expect them to make mistakes, preferentially at the low end. Oops, sorry. And that's exactly what you see. Okay. So the interesting thing about this is that if this is all correct, then it means that you can measure. The only thing you need to measure is the mode. Once you have the mode, you get the full distribution. And the mode, I think you can measure quite accurately. You know, which droplet do you get most often? The moment you measure that size, you've got the whole distribution. So I think Gareth's proposal is an important one. If it turns out to be right, then I think it's a big deal. And these mistakes matter, and they matter because the smaller droplets are particularly dangerous, because those are the ones that persist for longer in the air. So mistakes down at this end matter. This is the end that you're most likely to make mistakes. But if the universal distribution is correct, then you just measure the mode, and you can instantly tell how many droplets there are at this side. So I'm not going to go through that. Right. But of course, that assumes that the fragmentic liquid has no particles in them. Now, here's an interesting paper done by Anke Littner and Christian Wagner a few years ago. What they did was they took a Newtonian liquid, a highly viscous Newtonian liquid, but they put a small amount of 80 micron polystyrene particles in. Okay, so this is the silicone oil on its own, and this is the silicone oil with the 3% of polystyrene particles. And you can see when they put the thing into a capillary and watch how the capillary later fragments, you can tell the particles has had a major effect on the fragmentation process. There's not very many of them. It's not changing the viscosity it's changing viscosity by very little. Nevertheless, it has a major effect on how the thread thins down and then later fragments. What they did not tell us, because they didn't study it, is what happened to the particles. And so, you know, what happens if this is mucin? What happens if the liquid is not Newtonian but viscoelastic? And what happens if the particles are significantly smaller than 80 microns? Oops, sorry, I'm not meant to do that yet. So the question I want to ask here really is, if the presence of particles is coupled to the thinning and the fragmentation of the filament, then the distribution of particles in the final droplets may not in fact be uniform. Okay, so that adds a level of complication that I don't think anybody knows the answer to. Okay, so that's how these droplets may be produced, and I don't think anybody knows the full answer yet. You know, how did the presence of the viruses actually change the process that Gareth has studied? So I think the jury is out on how the viruses actually distributed in these droplets and what their actual size distribution is. So, but then let's plow on in our journey into ignorance. So what happens to these droplets the moment they are formed? So here's the major components of mucus, which is what makes out those droplets. So there's a lot of sodium, potassium, and potassium chloride and lactate. Those are the salts. These are the mucins, the glycoproteins. They didn't find very much DNA, but nevertheless, there's a lot of solids. Now, this is the only time in my seminar when I will quote quantum mechanics, because we live in a world, even though as soft metaphysicists, we like to pretend that H bar is zero. H bar isn't zero. I'll just pause for a second to ask you to let you think why H bar not equal to zero is important here. Because it turns out that almost the entire aerosol modeling industry pretend that H bar is zero. In other words, they ignore Pauli's exclusion principle. Pauli exclusion principle says electrons can't sit on top of each other, and therefore atoms can't sit on top of each other. And therefore, with this much solids in it, the droplets cannot evaporate to nothing. Okay, so all these are solids. And the solids eventually, at some point, Pauli comes in and they can't overlap. So solids have to take volume. So if you assume that the solids are completely close packed in the final droplets, you can do the calculation. You can check that any droplets with this composition cannot evaporate to zero, but can only evaporate to just under half of its initial radius. And that is very much non-zero. And most, if not all, of the modeling in the literature, that, you know, some very sophisticated modeling that takes into account the turbulence of the air jets and all the rest of it, do not take into account the fact that the droplets that we breathe out or sneeze out cannot shrink down to zero. But I'm going to quote a paper by Roland Netz later. He's one of the very few who has taken that into account, but perhaps in a way that can be improved. But I think this is important because, of course, you know, it is the small droplets that wreak the most havoc because they stay in the air for longest, and what constitutes the smallest droplets matter. Now, of course, this assumes complete drying. Okay, so I assume that all of the water goes away, and all you're left with are bits of these solids. But remember my Sherlock Holmes thing, if viruses survive in these droplets, almost certainly they cannot be completely dry because desiccated viruses explode. So let's think about what the presence of polymer may do in these respiratory droplets. So here's a very, very little known paper published in 2017. It's only been cited 3 times so far, and I think none of them has anything really to do with this paper. But it's done by a friend of mine in Bordeaux and 2 of his colleagues. And what Jean-Baptiste and his colleagues show, or the problem they solve, is this. Supposing you have a concentrated polymer solution and it's evaporating, so they are in the co-moving frame, so the interface comes down. No, sorry, they're not in the co-moving frame, they're in the lab frame, so the interface comes down. And so what they basically discover is this. If there's enough polymer in this liquid phase, the polymer all gets swept up. So if you like the Peckley number, if you put that slide there, it becomes a Peckley number. If the Peckley number is high enough, then a high concentration polymer polarization layer builds up at the interface. What goes on in this interfacial polarization layer does depend on the relative humidity of the gas, the relative humidity of the outside of the gas phase. But most of the bulk liquid here, sorry, let me say it again. But the actual rate of evaporation become controlled by mass transport in this bulk liquid phase, and therefore independent of relative humidity. Relative humidity only controls what happens in this layer, but it turns out that in a lot of circumstances, it's the transport here that matters. And so here is their prediction. For a thick film of a polymer solution, here's what happens if the solution is pure water. The evaporation rate, dimensionless, relative to plotted against relative humidity. So this is 80%, 60, 40, 20%. This is pure water. And this is what happens in their model when there's a high molecular weight polymer in the liquid phase. As you can see, by the time you get to even as humid as 80%, the difference can be order of magnitude. Okay, so let alone slightly drier. So what they find is that there's a very large bit of relative humidity space where the presence of the polymer renders the rate of evaporation practically independent of relative humidity, except very wet, and even in Scotland, the seldom get this wet. So let me now take you to the one paper that I found that does deal with the complex composition of these droplets. It is a very interesting paper published by Lindsay Marr from South Carolina in the Royal Society Interface. 2 years ago. Is it 2 years? Yes, it is about 2. Yes, it is 2 years ago. So what they did was they took a variety of droplets, but let me show you data for the droplets where they have reconstituted mucin. You can buy this stuff from Sigma Aldrich with sodium chloride at physiological concentration plus water. They make droplets, tens of nanometer, tens of micron droplets, and essentially measure their diameter as a function of the initial diameter. They deposit these on superhydrophobic surfaces. And so time goes this way. So in each data series, time goes along the curve. And these are the different relative humidities. And strikingly, they didn't comment on this, but strikingly, you see that over a very large range of relative humidities, until you get to below 50%, so from 90% to 50%, the evaporation rates are essentially relative humidity independent. That's exactly what Salmon et al.'s model would predict. So I would claim that this is prima facie evidence that the presence of a high molecular weight polymer makes a difference to the kinetics of these droplets. I don't know why at these lower relative humidities, suddenly the evaporation rate jumps up. A colleague of mine, Simon Titmuss, is now working on a calculation that he tells me might explain this. But I think this, I take as evidence that Salmon's model may have something to do with it. So that's one defect of these polymers possible. It would completely change the evaporation kinetics from what you might expect. But the mucin itself may also play the role of a hydrogel. And here, all you have to do is to think nappies. So, you take apart a disposable nappy, what you find inside is a polyelectrolyte hydrogel. I mean, this audit doesn't need me to tell you what happens and how it works. The dry stage can absorb a lot of water and hold to the water. I mean, this is known. So if you take microgel particles, we know that if you put microgel particles in the proper solvent where so that the charge groups ionize and the microgels swell, and you can make a space-filling sample. But what I want to ask you is to think through what happens. You try to take the water back out. You take all the water back out, it means that all the solvent ions would want to condense, and that entropic cost means that it basically would never happen. So I asked a whole bunch of people who have done electron microscopy on microgel particles, and I also looked into the literature. And it turns out it doesn't matter how hard you try. So this is one paper that explicitly reports this, but I'm sure there are others, that you take microgel particles, polyelectrolyte microgel particles, and you freeze dry them, which is a very severe form of drying. So you freeze it and you use a vacuum to sublime the ice. You freeze dry polyelectrolyte microgel particles. And what you find after prolonged freeze drying, there's some 10% of water left. And 10% is a lot more than a molecular layer on the mucin. This is a real amount of bulk water. And there are very few places on Earth when you can duplicate the humidity conditions of freeze drying. So what that tells me is that if you have a polyelectrolyte gel, such as may be formed by mucin, then it would be very, very hard to get rid of all the water because the polyelectrolytes would try to hold on to as much of the water as possible. And of course, there's soft matter knowledge on this. So my hypothesis is that the residual water, tens of percent maybe, in these in droplets of nose snot may in fact be absolutely crucial to the fact that the viruses apparently can survive and come to infect us. They are not desiccated. The complex nature of these droplets means that they probably hold on to a lot of water. So supposing Garrett is right, supposing this is the initial droplet distribution, the question is what happens next? Okay, so you sneeze them out, you get the initial droplet distribution. So the crucial thing here is a thing called the Wells evaporation falling curve, because it was done by a guy called Wells in the 40s. This is the original paper, well, not just 40s, 1934. So what this is that, so notice time goes from 0 to long times here, is in inverted time axis. So here is the curve of drops falling. So this is the time droplets of various sizes takes to fall to the ground from 2 meters high. Somehow the entire literature assumes that we are all tall Dutch people. In other words, our mouth is 2 meters above ground. I don't know why they choose 2 meters, but no one really has a nose that are 2 meters above ground, surely. But never mind, 2 meters is the industry standard calculation. Droplets come out to 2 meters. How long does it take to fall to the ground? This one assumes that they're rigid spheres. This one assumes that they get smaller and evaporate as they go along. but evaporating according to Maxwell's kinetics, your water drop can evaporate completely. This is the time to take droplets of various sizes to evaporate completely. And so the intersection represents the point at which, bigger than this, they fall to the ground before they completely evaporate, or in fact, we should take this curve means bigger than 165 microns, they fall to the ground before they completely evaporate, but smaller than 165 microns, they are still evaporating. They don't reach the ground, they completely evaporate before they reach the ground. So these curves are known as Wells evaporation falling curves, and there's a whole industry calculating these. But the important thing about these is that I only know of a single calculation, that's Roland Nett's one, that takes into account the fact that they cannot shrink to zero size. Okay, so you want to get this curve right, you have to take into account the fact that there are solids in there minimally, even if you don't take into account baby nappy physics, just Pauli exclusion principle, there are solids there, so the droplets cannot shrink to zero. To show you how important that may be, to take all these things into account, and also the fact that when you have solids in the drop, it changes the kinetics of evaporation. Lord Kelvin knew that, it's called the Kelvin effect. So I suggest you read this paper because I think it's one of the best papers that is published. Of the thousands and thousands of papers published from the physics point of view, this is one of the very best. So as I said, Roland included the effect of the solid, logarithmic slowing down evaporation and minimum volume, and also the fact that when the drops evaporate, they cool down. So he took all of that into account. Here, the 20-page of supplementary material is well worth reading. It's a sort of tour de force of theoretical physics. So here's what he's got. He's got time, and he's got droplet size. It doesn't look anything like my Wells evaporation falling curve until you realize that, of course, Roland is a physicist, not an environmental engineer. So his time goes from low to high this way, not low to high this way. And also he used a log scale. Okay, so you turn Roland's graph upside down and you begin to see, this sort of shape, and there's exactly this sort of shape. Okay, so these evaporate completely first and these fall to the ground first. And to show you that it matters, here's a 20 micron drop radius, and it takes 10 seconds before it hits the ground. Okay, so the scale here is 1 to 10 seconds. The relevant scale is 1 to 10 seconds. If you don't take all of this physics into account, you predict the scale of complete evaporation of a 40 micron, this is diameter, that's why it's 40 micron drop is all gone within 0.3 seconds. 0.3 and 3 is at least a factor of 10 difference, and possibly a lot bigger. So taking all of this physics into account absolutely matters if you want to know what happens to all the drops that you sneeze out. But my only critique of the Nett's paper is that he used a composition of saliva, and saliva has far less solids in it than nose snot, and so Roland's drops can get smaller before they stop evaporating than reality. So the actual effect would be even bigger than this, but it's important to put all the physics in. Now, what I'm going to do is I'm going to skip a whole lot of slides because I want to get to disinfection. So what I was originally going to show you is the only bit where I'm going to show you some of my own work. I'm just going to show you that when you put all the physics in, you can begin to simulate what happens to a drop, to drops that are sneezed out, and you can take into account the turbulent airflow and all the rest of it. But I don't have time to talk you through that because I want to take you to something else. Suffice it to say that if you want to do modeling of this kind, you really do have to put all the physics in, especially the evaporation of droplets are influenced by polymers and salts. So let me skip these. You can ask me about it later if you want to see those. So, but I want to get to disinfection and protection. So how do we kill? So, these viruses come out, they land on surfaces, they get through Mars and all the rest of it. So how may we protect ourselves? How may we kill these viruses outside the body? So I'm only going to say one thing because there's something extremely interesting in the literature that is long forgotten. So if you go back to some papers that have started to be published in the 40s, and this literature petered out and got completely forgotten by the 1970s, they did some very simple experiments, no genomics, no fancy sequencing DNA, no nothing. They simply took a solution of viruses and they bubble air through it. I hope they did not just get a graduate student and blow into a straw, but they basically bubble air, it might even be just nitrogen, bubble air through the, the virus, or they basically shake the hell out of it. And what they discover is that the virus, there are fewer and fewer viable viruses left in the solution. Okay, so this works for bacterial viruses, it works for human viruses, so it's definitely relevant. But and I've read the papers, they're very carefully done, it's definitely not fake news. But literally, it's all but forgotten. You talk to some even very knowledgeable virologists today, they don't know of this literature. But it was pointed out to me by a colleague, and I got extremely interested in what's going on. So interestingly, what especially this paper did was it very carefully rule out all kinds of other possible explanations. And that whole literature suggests that the common ingredients in these two is in fact the presence of air-water interfaces. So somehow when you generate a large amount of air-water interfaces, somehow you decrease the viable viral count. And you can think of all kinds of possible explanations. So, conceivably, when the viruses are swept up to the interface, they're lipid envelopes. I mean, we know that lipid vesicles unroll on air-water interfaces. So perhaps these viral envelopes actually unroll an air-water interface and kill the virus. But these are not just lipid vesicles, they have proteins in it. So we don't know how the proteins might affect this process. But we've also done just a little bit of theory work. It's mostly done by David Merenduzzo and Chris Brackley and Alex Morozov. But we also looked at the electrostatics of viruses. So, if you have negative RNA and positive protein, it forms an electrostatic bilayer. And as this virus goes close to the air-water interface, you can calculate the electrostatic self-energy of the virus. And what you find is the self-energy rockets up as you go near the air-water interface, because the fuel lines can escape into unscreened air. If you take into account the fact that the virus can provide a Pickering-type stabilization mechanism, this is the total energy, free energy of the virus as you approach the interface. Okay, so as you approach the interface, there's a little energy barrier due to electrostatics. And eventually, when you start hitting the interface and getting rid of air-water interface, there's a deep minimum. But the interesting thing is this barrier, the size of this barrier, is roughly the sort of energy that you may expect in shaking or bubbling air. So the flows that are generated may be enough to help the virus to overcome this barrier, get them to the interface where the electrostatic self-energy may just blow it up. Anyway, so I think I am actually, no, sorry, stop slightly too early. I think I'm actually done. Let me just go to conclusions. So the transmission of this virus involves a lot of soft matter physics, especially I think the behavior of these complicated droplets is a wide open field. The mechanism of viral deactivation, how the soap actually destroyed the virus or how these interfaces do it. So basically, I've convinced you that there are many other, well, I mean, I haven't convinced you, but I can tell you that there are many other areas of application of physics to COVID, including how to use statistical physics to think about epidemiology. So my message is don't leave it all to the biologists and biotechnologists. Soft matter physicists have a lot to contribute. And I think that is actually it. Yep, I'm done.
Oh, bravo. Thank you very much. So we should open the talk up to questions. And I'm inclined to jump in, but I want to give people a chance to settle their thoughts and start asking.
I would just say that the analysis about droplets reminds me a lot of the same physics involved in ocean spray and why droplets there persist more than you might expect. It's essentially the same idea.
Is that plus? Because the salt doesn't necessarily also have these, layer effect on the outside, but yes, it points in that direction and beyond it. Yeah.
So a couple of questions. First of all, do you think this explains the temperature effect that has been, that's been kind of observed and speculated on quite a bit, at least in the early part of the pandemic, the temperature effect on on the prevalence and the effect of the pandemic. And the second question is, it basically safe to think of them, to think of the particles as tiny hydrogel balls, essentially, because you wanted us to develop a mental image. And I think this is kind of the mental image I'm going with.
So I mean, the second question is easier. That is certainly how I have now started to think about them. I want to think about them as, 50 micron hydrogel balls. And my hope, if I manage to get the money to start a program, is to do the basic physics of these hydrogel balls using a model system. And that is relevant to your first question, because if you do these public health studies without understanding the basic physics, every new paper contributes to the confusion and not to the solution. Basically, because we do not know what the basic physics variables are. If I don't know what the variables are, I never know whether I have controlled all the other variables and only changed the one I want to change. So someone studies the effect of temperature, but who knows what all the other variables are that you have kept constant or not kept constant? I mean, that's time and again the same in the history of science. Until you have a basic physics picture, experiments in a multivariable situation would only add to the confusion, because you never know whether you have controlled the variables. So I think the literature is completely confused, because if you look at the literature on relative humidity effect on flu, there are many, many different kinds of reports. And I think that's because they don't know what variables they're controlling. So I want to do the basic physics first and ask, because if I do a model system, there are only 4 variables, and I know what they are because I made the system. Once I know those, and I want to go back to the literature. So at the moment, I don't know how to interpret the literature. There are too many variables. But I think someone was trying to come in just now.
Yeah, that was me. I was trying to rudely interrupt. I'm sorry. I wanted to ask you,
No,
if you were to put your hand in the fire, despite what you just said, then what would the prediction be with respect to the effect of salt? And if you go from summer to winter, would you predict that cold temperatures as a function of your 2 variables, the humidity and the salt concentration, would they make the droplets persist longer?
Yeah. I mean, I'm not sitting on the fence. I simply do not know, because I don't have an intuition of how because this is not just ocean spray. I agree ocean spray physics matters, but what is on top of this is a 20 million molecular weight polymer. And there genuinely is very little guidance out there in the literature to guide my intuition on what happens when you have that drop. And in fact, interestingly, if you read that Marr paper from wherever it is, Royal Society Interface, when they also add some lipids in, it dramatically lowered the evaporation rate. And these droplets undoubtedly have lipids in them. So yet again, the lipids would coat the outside of the drop, and you can imagine why that would dramatically change the evaporation rate. And the reason why I hesitate is that even lipid phase behavior may come into here, because if you get really cold, the DBPC, DBPE, and all the rest of it would undergo a phase transition from the L alpha to the L beta solid phase, and that would dramatically affect the evaporation rate. So I just simply, having not done the model experiments, I really do not know which bits of physics actually dominate. And that's why I'm not guessing. I really have no idea.
Okay.
I mean, someone ought to do this quickly and find out. But what I want to stress is this is not only relevant for COVID, it's definitely relevant for flu, because it's generic physics.
But it's quite bad news, right?
Sorry, I didn't hear either.
Well, the fact that there's gels and the fact that what you're saying about the evaporation rate overall is bad news.
It is very bad news, because if you really are these gel balls holding a lot of water protecting the virus, it is very bad news indeed, but we might as well know. And I mean, look, let me give you a clue why we should have always known that water is important. Because people keep saying that copper door handles and copper furniture, copper surfaces are very good at killing, viruses, viral contamination. People have known that for a long time. How does that happen? It's copper ions that kill viruses and bacteria. The only way you can get copper ions out of solid copper is that the viruses must be surrounded by water. So we should have known all along that the viruses do not land and survive on surfaces as bare viruses. They must land on surfaces and survive as viruses surrounded by water. Otherwise, there's no way a copper surface can kill viruses.
So Wilson, you would say that that essentially the way it's spread is mostly by surfaces. Is that right? Not by the aerosol. It's not by breathing the aerosol.
I don't want to give that impression. I think the way it spreads is mostly by polyelectrolyte microgel balls. Whether it is
right, but where are they? Are they in the air or on the surfaces? Have they sedimented? Is it mostly by?
I can only rely on the consensus. The consensus at the moment seems to be it is mostly through air for this virus.
But 750 micron particles don't survive that long, right, in air, as you showed. Second.
Right. So, okay, so if they start over 50 microns, so let's work this out. So a 0.5 micron drop on average would have at most, sorry, a 5 micron drop would have on average 0.1 virus in it. Okay, so the lows are rather low. So if you take the peak viral load they have detected in the nasal fluids of COVID patients, a 5 micron drop would have 0.1 virus on average, partial distributed, okay? So that sets the scale. So how big a droplet can survive in the air? 5 microns, right? 5 micron may survive in the air.
Yeah.
You agree? Okay, so that means that drop started off as a 10 micron drop, right? Because they shrink to half the size. So 10 micron drop initially would have about, what's 0.1, is about one virus in it. So I do have some difficulties about the numbers.
And the number of for the infection of 1,000 is a good number. You need like 1,000 viruses to do.
No one knows it for. No one's claimed to know it for SARS-CoV-2 yet. The 1,000 is a consensus for flu.
You think it's also a consensus for COVID, but that's just from reading a couple papers. Those are the numbers they use.
The consensus is a lot more than 2 papers. So I don't know is the answer to that. But if you need 1,000, you need to work on the numbers because the numbers are low. The average number of viruses in the droplets that may survive in the air is low. So it bothers me. I mean, I've been talking about this with Dan Franco, and it bothers both of us.
Well, that's an endorsement.
Oh no, I'm very proud that Dan was bothered by this. Yes, I agree.
Can I ask you a question of numbers? I may have misheard your numbers, but you mentioned, I think, 2 numbers. You said it's polymer of 20 millions molecular weight. And you also showed the picture of someone sneezing with a line extending for 10 centimeters or so. And you said it's a long polymer. So if it is 20 million molecular weight, it's not 10 centimeters. It's at least 2 orders of magnitude shorter. So how?
Well, I think molecular weight can go up to 200 million.
200 million. Okay, then.
I think 200 million. You can certainly get to 1 centimeter, but I might have done my sum wrong.
200 meter. Yes, it's 1 centimeter. Right.
I believe that mucin can go up to 200 million, and my slide says up to 200 million.
Okay, but still it's not 10 centimeters. So it's probably not a single polymer. It's something else. It's some.
There may be a few polymers with some sticky ends that are sticking to each other,
right,
or something like that.
So it's more complex than just a polymer.
Okay, so it's a few polymers all stretched out and sticking to each other. Okay.
I have a small question, maybe somewhat linked to this single versus bundles of polymers, but through the virus. You said, well, how do we imagine the virus? How do we imagine transmission? And I think most people, when they think about a virus, they think about this, discrete thing, this one virus, one particle. I'm not sure it's true, and I think that anyone who worked in soft matter know how hard it is to stabilize particles definitely on that length scale. So are viruses really discrete, or they are patches? They are kind of, how should we think about that?
I think the answer, yet again, is almost largely unknown because almost no one has ever studied it. But that is partly because usually the volume fractions that we're dealing with are very low. So we're dealing with volume fractions of 10 to the minus a high power. So, you know, they would almost never find each other to aggregate.
Except
When they come out of the bacteria, they are very concentrated.
I agree with that. David was trying to say something.
Oh yeah, no, I was saying the same thing that Matan was saying, that you know, that they get concentrated on surfaces. I was actually thinking that what you've told us today provides practical guidance for people who are trying to make personal protective equipment. So it raises questions like, is spun polyester a good material for masks? And based on what you told us, it sort of sounds like it is, because it's not so much a desiccant as just something that will hold the fluids in place, or at least redirect the flow of particles. Is that how I should think about it?
Well, but I mean, the question is it fluid? Because, I mean, at the moment, I must admit my own personal favorite picture, based on almost no evidence, is the virus is encased in a glassy polymer matrix. So in other words, I'm imagining the mucin eventually glassifies. So I think glassy polymer may be a slightly better picture than a gel. But I have almost no evidence for this, but I mean, that is my current prejudice.
If that's the case, then imagine you're infected and you're wearing a mask. How, you know, does that mean that your mask will now become a biohazard for a relatively long period?
Presumably.
Jeepers. Because
I mean, I don't know what I said is true, by the way.
Re-wearing our
you know,
masks day in, day out.
Work on. But I think it also matters about a time scale, right? So the interesting thing is, you know, you imagine it transmitting through the air, right? How long does it take to reach that vitrified state? Because if it reaches the vitrified state before it gets into my nose again to infect me, what is interesting is that then you have to imagine the water vapors inside my nose plasticizing that polymer glass. Right, so there's a replasticizing time scale. And this is all good classical polymer physics that, you know, we need to go and put into the problem. But it may be relevant. Polymer glasses may well be relevant here. I don't know the answer to that, but it certainly be relevant on a surface. If it sits there for long enough, how else am I supposed to think about it? Eventually, the mucin reach some glassy state, presumably. What I don't know is what all that salt does.
And so even in that glassy state, though, it remains a viable medium for the virus. Like, it would be fine if it desiccates to a state where the virus disintegrates anyway.
Well, so again, I'm going to keep saying it. I have no idea, simply because there's no literature whatsoever to guide me on what may happen to a virus in a polymer glass and what the state of water is. I mean, there's a lot of water in there. So the polymer glass may yet, you know, is the water free? I mean, is the water in a liquid state? I don't know the answer to that, but someone may. I mean, I just want to take a drop of my nose snot, dry it, and see how much water is left, right? I mean, that shouldn't be too difficult, but I need to do it in a controlled way.
These would be difficult grant proposals to write under normal circumstances.
Yes.
Cynthia,
want to say something, right?
Well, I was going to ask a nose-related question, which is the relative humidity may not affect the evaporation rate of the droplets, but it could affect how they interact with the nose once they get back in there. So that could be where the winter versus summer is more important.
Right. That may very well be the case. The moment you start thinking about these drops as complicated as that, it affects the entire journey. You know, it affects the way you think about and do order of magnitude estimates for every single bit of the journey until the second person gets infected. And the frightening thing is no one has done it. I mean, there literally is zero literature on the subject except that one paper I quote from Journal Royal Society Interface. soft matter physicists of the world unite. We need to solve this problem before the next pandemic.
Okay. Hello. I have one small question. For the meniscus, it contains a lot of components like the virus and the polymers. So does it interact with each other in the meniscus? And when it's formed the thread, does the interaction influence the extensional rheology of the fluids or not? And how does it influence the distribution of the drop?
It may be a small question for you, but answering it would be a giant step for mankind. The answer is I have no idea.
Okay.
But it's a good question.
I got a good question about, I don't know, about the fluids. Actually, you mentioned mucus a lot, and then saliva about Netz's paper. So could you comment more about the two, the difference in terms of all the things you explained, and when each of them are relevant?
Thank goodness someone asked me a question that I actually know the answer to. This is fantastic. The answer is I do know. And if you look up the relative composition of saliva, it has far less solids in it. So the amount of actual, if you just sum up all the solid component, solid is the wrong word. If you sum up all the non-volatile components of saliva, it comes to about 1% of the drop of the initial. So in Rowland's calculation, because you use saliva, the drops can shrink to about by about 90% or more. And I checked that is the correct composition of saliva, that he has used the correct composition of saliva. And it simply has less proteins in it.
So then what?
I checked, that is genuinely the case.
And in terms of virus survival, would that make any difference?
So, I presume so, because if you have less protein, then your ability to hold on to water may well change. Right, because in my hypothesis, the holding on to water is largely because of the polymer, because of the polyelectrolyte. So you have less polyelectrolyte, then, again, then you're soon taking me into territory. The answer is I don't know, but I believe that the things that we sneeze out is largely respiratory mucus and not saliva mucus.
Yeah.
I have no idea why Roland use saliva. I keep meaning to email him and ask him, but
okay. But if you think in terms of asymptomatic spreading, for instance, then it's not so much sneezing and coughing that matters.
Then it's breathing and speaking, yes.
Yep.
But I think, and again here, I have not looked into literature enough, but I think even speaking, most of the droplets or originate down here rather than in the mouth. So again, that's something that I don't know the answer to.
Okay.
But certainly, insofar as there's literature on respiratory droplets for flu, they tend to use they all use the composition of nasal mucus rather than saliva. Of course, they could all be wrong, but that's what the literature does. But it is genuinely true that saliva has far less non-volatile components in it than respiratory mucus. I think that must be the case, because if there's that much solids in saliva, very soon our saliva may feel very lumpy. Right? If the saliva just evaporates a tiny bit on the tongue, it will feel very, very gritty on the tongue, and that certainly isn't the case. So I can believe that saliva doesn't have quite as much non-volatile components in it. It's just from experience on my own tongue.
Okay, thanks.
So are there more questions? Because I think what we might do is thank Wilson one more time and then stop the recording after we point out that this is the final CSMR soft matter seminar in the series. We'll reconvene at the end of January. Everybody's invited and you're all very welcome. And I want you all to take Wilson's lessons in hand. Stay safe, enjoy yourself, have a terrific holiday season. And I guess the idea is wear your mask, wash your hands, maintain social distancing for all the reasons that we've just heard. So I'm going to stop the recording.